Welcome to this week's lesson of Computer Science Club. Today we're going to be going over a question that we had last week, and it is called DMLPC 15C4P4, and it is the great sequence question. 1 second. Okay. So the question says, given a sequence of n integers, determine the subsequence from x to y inclusive is a great sequence. A great sequence is a sequence whose sum is strictly greater than k. Luke thought this was too easy, so he'd like to know if the subsequence is an amazing sequence, which is a great sequence in which the integers a and b appear. Given his original sequence, he'd like to answer Q queries, determining if the subsequence is an amazing sequence. Alright, so for this problem, you've probably seen the first half of the problem before. The first half being the qualifications for a great sequence. And that being in your prefix summary lesson that you had with David two or 3 months back. I can't remember. So that part of the question is a bit easier. Whereas the second part of the question, which is saying if the integers a and b appear, this is the part where the binary search will come in, and so that's what you're gonna have to use to solve this question. And it's gonna be an interesting way to solve the question, but nonetheless, it should still work. Okay, so we're gonna go right into the take up of this problem, because it was definitely one of the harder problems on there. So it's good that we're taking it up right now, just so we don't have to stress about not being able to solve it, because if you can do this question, you can probably do most of the other questions. So if you can understand the ideas of this question and see the binary search implemented into it, then maybe you'll have some inspiration in some way of saying, okay, now how do I apply this concept to another question? So we'll go ahead and get started. Let me just save my file, and we'll call it March, and today's, it's going to be the 26th when the video comes out, March 26th, binary search take up. Alright, let's get started. Let's remember our template code should always be include bits /std++.h and then using namespace, I can't type, using namespace std int main. And then I'm going to put my fast input in comments here, because I don't want to, when I'm testing my program, I want to make sure that I can see all the input and output when I want to, not like all at the end, because that's how the tie works. Okay, so we have some pretty big numbers. The k is pretty big. AI and BI, the numbers in the array are relatively small, and then the size of the array is 1,000 for the first subtask and 100,000 for the second subtask. So we're just going to go and solve the second subtask. But since we're going to be typing long longs a lot, because we're going to be dealing with numbers up to the size of 10 to the 9 in both positive and negative direction, then we'll want to store our prefix summary as a long long. And at the same time, we'll store our original array as a long long array as well, because why not? All right, so we'll have our initial array as, actually we should define our max n size. So this is to bypass the problem where this gets highlighted because it's not a constant size. So we're going to set the size to be around 100,000, and we're just going to do 5 more just for good measure. And then the regular array and then the prefix sum array, or as I like to call it, PSA. So we have the regular array and the prefix sum array in there, and then we need int n in q, and then long long k. And then after, we can handle everything out in the int main. Alright, so now we can take in our input, nkq, I believe? Yeah, nkq, sorry. nkq, and then after, what we're going to do is, first we'll just get all of our input in and then do the prefix summary checking to get make sure that's working. So for int I, and since the constraints go from 1 to n, the indexes in the array, the xi and yi, we're just going to use one indexing. So we're going to loop from 1 to n and including n. So for int I equals 1, I is less than or equal to n, I plus plus. And then we take in the array at I. And then the prefix sum array at the spot I equals the sum of the first I minus 1 elements plus the current element. And that looks like so. And then after, we can go do our check. So over here, you're going to be given 4 numbers, I believe, AI, BI, XI, XI, YI. So we're going to have that in as int AI, BI, XI, YI. And then, so we're going to have Q query, so we'll have a lowercase q for int Q equals 0, Q is less than Q, Q plus plus. The Q variable is going to be useless, but we just need to loop through Q times, and this is just an intuitive way to do it. So Cn, AI, BI, XI, YI. And then if PSA at yi minus PSA at xi minus 1, because you're saying the sum of the first yi numbers minus the sum of the first xi minus 1 numbers, and that will leave you with the sum of the numbers from xi to yi inclusive. And if that's greater than k, because the question, the great sequence requirement is that strictly greater than k, then we are good to go. We can say yes, and then move on to the next query. Keep in mind, this is not the full question at all. We have to do the entire binary search part, but this is just the prefix summary part. Make sure that's working. All right, so now that we have this working, we can go ahead and do our binary search. And so what we're trying to search for is in our range x and y. So our bounds are x and y, or xi and yi. We need to check to make sure that there's a value of a in between xi and yi, and there's a value of b between xi and yi in this array down here. And if there's not, then that means that we can conclude that it doesn't appear. Therefore, the condition is not satisfied. Note that we have AI and BI is between -1000 and 1000. So to counteract the problem of negative indexing, we're going to assign AI and BI to be 1000 more than what they were before. So over here, when we do our processing, we're going to do AI plus or equals 1000 and BI plus or equals 1000. Okay, and then we're going to do our once we do our check in there, that'll be fine. But and then over here, we can't do our array at I plus or equals 1000, otherwise I'll change the total sum. But when we go ahead and put in a frequency array, which we're going to have to create, then we can go ahead and do that. Or it's actually a frequency vector array. So we should get into that right now. So since we're looking for the since we're looking to see if a value of AI and BI are both in between the range xi and yi, the binary search in this case is going to be storing all the frequencies of all the numbers, like all the possible numbers, so from -1000 to 1000, and then with each individual query, which is taking AI, we do binary search inside of like you store the frequency is going to store the indexes. Which indexes in the array are going to be equal to AI, or for equal to -1000, -999, -998, so on all the way to 998, 999, 1000. And so when we do a binary search, we're asking, is there a number in this frequency array at AI that is in between xi and yi? Or in the sense that could also mean, is there a number in between xi and yi, or greater than or equal to xi but less than or equal to yi? Is there a value of AI in that range somewhere? And so that's going to be what our frequency array is working with. So let's actually go ahead and create that frequency array right now. So we want this thing to grow for each value between -1000 and 1000, but there are a fixed number of them, because you're going to have a frequency array from -1000, -999, -998, all the way to 1000. So that's 2001 total things. But we're going to go a little more. So we're going to call it vector int frequency, and the size will be 2005. So note that when I put anything in square brackets, it converts the original type into an array. So the vector ints, that means there'll be 2005 vector ints. And remember how I did plus 1000, plus or equals 1000, plus or equals 1000? This is why, because you can't do frequency at negative 1000. Your frequency, your indexes have to be between 0 and the size of the array, like the size of the array minus 1, or the size of the vector minus 1. And so when we go and insert the fact that there's a frequency of array I inside the frequency array, we're not going to push back, we're not going to just do this, but we're just do frequency array I dot pushback I. I is a spot. We want to keep that. But the thing is, this array I can be negative 1000 to 1000, so we're going to change that from negative 1000 to 0 by adding 1000, and 1000 to 2000 by adding 1000. So those are going to be the limits. That's why my size is 2005. So frequency of array of I plus 1000, this will guarantee it's going to be in the positives, dot pushback I. And so now we got our frequency array working. And so now we need to do a binary search test for this condition over here, because this isn't the only thing that requires to have an amazing sequence. We need to have the binary search for the frequency of the AI value, if there's a value in between xi and yi, where one of the indexes is between there, but it's for AI, and then one for bi. And if both those conditions satisfied, then we're good. So let's go ahead and see what that's going to look like. So we're going to have a Boolean function, and we're going to call it Boolean B search. And then we'll have the value that we're looking for, the query range, so it's going to be QL, and then QR. So it's going to be the query left and then the query right. And then now we can go ahead and start a binary search. This is similar to last week. So our limits to this binary search, the left and right values we're going to start with are int L equals 0, because you always start at the very left, which is 0. And then right is the rightmost index in frequency at val. So it's going to be frequency at val dot size. And then you have to do -1, because if there's 1 element, the indexes are 0. If there's 5 elements, the indexes are 0, 1, 2, 3, 4. So it's always frequency val dot size -1. All right, and then now we can just take our mid value, int mid equals L plus R divided by 2. This is similar to last week. All right, so now we will keep searching while L is less than or equal to R. And then we will get mid is equal to L plus R over 2. Actually, we don't need to calculate mid over here. Let's just get that out of there, so it's unnecessary. It wouldn't really stop us with anything though. All right, so we have mid equals L plus R over 2, so again the middle index, and then now you check with that middle index, is it between QL and QR? And then that's as simple as if frequency at val at mid is greater than or equal to QL, and frequency at val at mid is less than or equal to QR. So if it's greater than or equal to QL and less than or equal to QR, it's going to be between QL and QR, and you can include both ends. And if so, then that means we found a required thing. We can return true, meaning that it exists. There's one in there. Otherwise, there's two conditions. Else, if frequency at val at mid is less than QL, that means that you're too far to the left. Your mid value is too far to the left, and then now you need to bring your left value over to mid plus 1. So you're searching on the entire right side of the of what you're searching of before, the right half of what you're searching of before. And then otherwise, and that means that you're too far to the right, so then it's just going to be R equals mid minus 1. And so at this point, if you didn't find your value, that means that it either didn't exist or your frequency was empty. In either case, we should return false here, because that means that there's no value equal to val that's in between QL and QR in the regular array. So that's the binary search. So now we can go ahead and just add this to our if statement. So we do and binary search of, and make sure that we're passing AI and BI, which are already incremented by 1,000. So we can just do AI, and then the limits, the left and right values are xi and yi, and then these limits are bi, xi, and yi. And so now we've satisfied all the conditions. So let's test this out and see if it works. Let me just copy this sample data right here. I really hope this works because I don't see anything I did wrong. But yeah, let's give it a shot. So this data over here, let's copy it here. So we have a yes, yes, and a no. And the data over here suggests that the sample output should be yes, yes, and no. So let's try submitting this. Let's give in our fast input because we don't want it to TLB just because of fast input and not know that. So once we submit it, just copy and paste the code and run the submission. All right, so as you can see, it's running really fast, and we completed all test cases with the worst case being 0.042 seconds, and the worst case memory was 5.36 megabytes. So that's a solution to this problem. It's pretty basic, but I understand why this might have been confusing, because if you did this question even slightly unoptimized, you would have gotten a wrong answer. I was trying to do this question before I came here just to get a refresher, and it took me a lot of tries because I was doing something that was horribly inefficient with copying values. So yeah, this question was sort of difficult. So yeah, and especially with binary search being new to most of you, I completely understand why many of you didn't attempt this question. But here's a good solution to the problem. I'll be posting it on our GitHub. And for this week, I don't want to teach a new lesson because I want you guys to keep working on those problems. I might post more binary search problems if I can find them, because it's really important that you get practice with binary search. Because yeah, it's a really, really important topic, and unlike most algorithms, you're actually going to see it in the everyday world. So yeah, that's it for this week. Hopefully you guys enjoyed. Make sure you guys study for your exams. Make sure you guys do well in your classes. I'm pretty sure we're going to be canceling the next few weeks because of exams and the spring break. But we'll keep you guys updated. And yeah, that's it for this week. Hopefully you learned how to do this question. Hopefully you have an idea of how to do binary search. And then now you can attempt the other questions. All right. See you.